Good afternoon, YouTubers. My name is Rod Macduff. I'm speaking to you from Perth in Western Australia, and this afternoon I'm going to talk about the QMAC HF-90 radio. This little radio here that I designed over 20 years ago, and that was manufactured by QMAC Electronics for approximately 15 years. The HF-90 radio is a shortwave radio. That means it's suitable for long-distance communications. It was typically used by aid agencies, four-wheel drivers in Australia, and also military in many countries in the world. There were approximately 10,000 of these radios manufactured over a period of 15 years, and they were sold to 120 different countries. So in the first slide, you'll see it's titled Radio Design and Value Engineering Concept to Reality. On the left-hand side, you'll see an image of the concept model or space model. That was the volumetric model for marketing purposes that showed roughly what the radio would look like in order to test the market. It didn't contain any electronics other than some LEDs to illuminate the frequency display. On the right hand side you can see the realized radio as it was first rolling off the production lines in 1996. Now, it's no accident that this radio looks a bit like some of the earlier rationale radios. It's got that little red window in its face, and it's got the two protective handle ears that render it rugged. I worked for rationale for nearly 10 years in the 70s and 80s as a design engineer on the HF-90 team, and that company was extremely successful at marketing military HF and VHF radios, and so I learned a lot when working for rationale. The next slide gives you a bit of a window on how the radio was prototyped. On the left hand side you can see a very early prototype of the radio. The front panel was always actual size, and the microprocessor board was always the Eurocard 160mm by 100mm format. The microprocessor board was realized by using a thing called the Vero-wire system. IC sockets were put topside, and underside had a kind of plastic comb system, and wires were wired point to point using that comb system. All the radio frequency development was done using ugly construction on double-sided PCB. Now, many of you will be familiar with ugly construction. All the ICs are mounted upside down, and then through-hole and surface mount components are strapped from the pins to ground or to other points, giving a very low impedance to ground construction and also relatively direct. So it's quite a low noise method of prototyping. It's relatively repeatable and reliable. You can see different boards here. Right up at the top center you can just see the heatsink of the PA board popping out. Right from that you've got the 5V power converter. You can see HF-90 synthesizer labelled. That was an earlier chip. And then you've got the 50V switching power supply underneath the PA PCB there, feeding the 50V to the final. And then you've got the HF-90 receiver under there with the high third order intercept mixer off to the bottom right hand side. So that's pretty much all of the PCBs apart from the output harmonic filters. And so all of that had to be crammed into what was finally realized on the right hand side. Top right hand side, you can see top side of the power amplifier switch mode power supply board, and then beneath that you have got the underside PCB, which is the receiver microprocessor board, and you can see what these look like when they're finished and neat. Before designing the HF-90, we had a look at lots of other radios that were in the marketplace. Radios from Harris, from Mycom, from Plessey, Raycal, Kodan and Barrett, and others besides, particularly amateur radio offerings. And we also talked to the users about what they liked and didn't like about these. Now, the British Army experience with Bowman was not a happy one. In fact, the squaddies said that Bowman should stand for Better Off with Map and Nokia. That's because they found the radios terribly difficult to operate. They were unnecessarily overcomplicated. And so one of the driving forces behind the genesis of the HF-90 was that it should be simple to operate. Consequently, it's only got 6 buttons. You've got the channel up and down button, you've got the mode button, which in frequency hopping radios selects frequency hopping. You get a tune button, although it auto tunes, so you don't necessarily need to use that button. And then there's the clarifier buttons up and down, which are virtually never used. So in fact, there's really only 2 or 3 buttons actually used by the operator. And then there's the traditional volume control and the on-off switch. So very little in the way of user interface there. Yeah, the second thing had to be low weight, looking for about 1 kilogram. In fact, that was the realized weight. Third item was that it had to be easy to service. The radio had to be easy to get into. I've just taken the 4 screws out, and it also had to be easy to swap a board. And in fact, there are only 3 PCBs. There's inside there's the display PCB, and there's the power amplifier switch mode power supply on this side, and there's the receiver microprocessor board there. So changing a board is as simple as prizing them apart like that, and then you put it back together again. So extremely simple to service. Probing and access is also extremely easy because there were plenty of test points. The critical test points were brought out to 2 rows top side on both the receiver board here and on the PA board here. Another critical item was that parts should be cheap and readily available. One thing that I experienced when visiting overseas repair workshops was that you'd see so many radios there just lying open, and I would ask the service personnel, what's the problem? They said, can't get parts. These are custom parts from the manufacturers and we just can't get hold of them. So design philosophy for the HF-90 was that basically anything used should be available in the radio spares or Farnell catalogue. So jelly bean components. The next design idea was for low inventory. Because QMAC was a very small company, we didn't want huge volumes of components in stores. And so one of the tricks to minimize inventory was that instead of using E12 or E24 resistors or capacitors, where you have say 12 different values for every decade, there's no reason why you can't use E2, which means that for every decade you've only got say 100k and 330k resistor. And if you want values in between, you can series or parallel. They're so cheap that there's no reason you can't do that. And incidentally, it also increases reliability very slightly, because if you have a component go open circuit and you've realized it through a series parallel arrangement, then there may well be a resistor still in circuit, and so it'll continue to operate. Another design cornerstone was for simple design and functionality, maximum functionality implemented in software. I'll say a bit about this later, but the ZX81 was a case in point in simple design and functionality, where as much as possible was relegated to software. And that's exactly what was done with the HF-90. Finally, because the parts were to be readily available, they also needed to be multi-sourced. So a microprocessor was chosen that had at least 7 different vendors, 7 different manufacturers. And that led inevitably to a long manufacturing life. HF-90 was manufactured for over 15 years, which is quite remarkable for an electronic product. Your typical mobile phone is only manufactured for 2 years. And so to be able to achieve a 15-year manufactured life speaks well to the choice of components, because they were able to be procured over a long time. Now we'll have a look at the technical specification. It's an HF radio covering 2 to 30 megahertz in 100 hertz steps. It offers USB, LSB, CW or Morse code, and frequency hopping. It operates on a 12 to 20 volt power supply. Now that's very useful if you want to install it in, say, tanks or trucks, and in fact it does operate up to 28 volts, so you can operate it in aircraft or helicopters as well. Not having to have any power converter is very useful. And the receive drain was 300 milliamps and the transmit up to 10 amps. Being aimed at the military market, it has to cover minus 30C to plus 80C. That was realizable with standard ICs and sensibly rated electrolytic capacitors. On transmit, it will realize 50 watts PEP up to 12 megahertz, and above that the power is derated. Now that isn't a particular issue, simply because the tactical radio band only goes up to 12 megahertz. Most military radio operators are using near vertical incidence skywave, short hop, and so they're not using frequencies much above 9 megahertz. Another critical thing, in the electronic warfare scenario, you really need a high third order intercept, and a third order intercept that was realized for the HF-90 was plus 20 dBm. I'll speak a bit more about that later, but it basically means that when you're in a very crowded strong signal environment, the radio isn't susceptible to interference. The transmit intermodulation was minus 23 dB, which is absolutely standard. RX sensitivity, 1/4 of a microvolt for 10 dB cyanide, that's also pretty standard. And as said earlier, the weight is coming in at 1 kilogram. These slides look at the design steps necessary in order to actually realize the HF-90. Now, the first step that we took was to determine the size of the radio. The target weight was 1 kilogram, and we thought that we could get it inside a case that would accommodate a standard 160 millimeter long by 100 millimeter wide Eurocard. Now these cases were called link cases. They were extruded aluminium cases and extremely robust. The next step after that was to determine the electronic functional blocks. And then it was necessary to determine the IF frequencies and the synthesizer architecture. After that, chose a microprocessor, chose other chips, and then did a rough board layout with a signal flow in order to guesstimate whether it would actually fit in the on the 260 by 100 millimeter Eurocards. So these are some of the key design decisions taken in designing the HF-90. Decided to use a signal architecture where all mixers were used both on receive and transmit. So all the mixers had to be bidirectional, as the signal flow would reverse through them when it was toggled from receive to transmit. At the time, 455 kc ceramic filters were relatively cheap, so it was decided to use a standard high-spec 455 SSB filter to realise the selectivity. This was in a time before software-defined radio. For the first IF, an 83 meg IF was chosen because there was ready availability of SAW filters, 30 kilohertz wide, that gave that roofing filter relatively cheaply in order to realise selectivity at the first IF. Now the first mixer, it was decided to use gas FETs as passive switches for high intercept performance. These gas FETs were available from satellite television technology. They're manufactured in very high volumes, so they're available also at low cost. So all these components were thrown up by the technology boom in the 80s that gave rise to these very low cost high spec components, and so great use was made of these. Now these also included frequency synthesizers, dual synthesizers that were available from Motorola in order to, these were originally used in mobile phones, and they were reapplied in the HF-90 radio. And I'll say a bit more about the magic number technique for realizing fast locking and low noise. But these synthesizer chips lent themselves well to that technique. Other decision was to select high-level FET local oscillators. Using a high-level oscillator gives rise to a lower phase noise. Also used a standard consumer AM radio, 455 gain block in the receiver, and that was a convenient way of compactly and cost effectively getting controlled gain block for the SSB receiver. Next, chose a very low cost multi-source micro, the ATC51 micro, which had been available for some time, had a lot of easily available code, and also was available from 7 different manufacturers. And so through using that microprocessor and making it work extremely hard through clever programming, it was possible to squeeze the absolute maximum out of it. As far as the power amplifier, the RF power amplifier is concerned, that used a standard off-the-shelf heatsink, which made it easy to prototype. Also, it used standard high voltage MOSFETs, the IRF 830 MOSFET. That made it possible to run the PA at a 50 volt rail. Now, running a higher rail, you tend to get lower intermodulation distortion, and also relatively easy output matching. Because notionally 50 volts, 1 amp, 50 watts, 50 ohms, so it's too easy to match it really. Next, in order to generate the 50 volt rail, I used a switch mode power supply on transmit, and that allowed the use of 12 volts or 24 volt DC in to feed the radio. Also, it's decided to put the RX and TX PCBs back to back with ground plane on the underside for maximum screening. And you'll see here, these are the undersides of the two PCBs, and you can see they have ground plane on virtually all of the underside. They're only 2-layer PCBs, so relatively cheap to manufacture, and all the signal and power traces are topside. So tricky to lay out, but once done, low cost manufacture. Here we see the system diagram for the HF-90. At the bottom is the ATC51 microprocessor. That has onboard flash memory with the code on it, and there's an external memory to contain all the channel data. An incremental shaft encoder controls the volume, and 3x2 matrix takes the push button information to the microprocessor. Serial shift registers take the data out to the display, and there's also inputs to the microprocessor from a signal strength level meter, and also a data slicer in order to process cell call and frequency hopping synchronization data. You'll see a series of 3 mixers and 3 oscillators. The 3 mixers have got the X symbol, and the 3 oscillators are simple circles. The oscillator on the extreme left-hand side is the one that runs at between 86 and 113 megs in order to mix down to the first IF of 83161 megs. You'll see a dual synthesizer controls both that first local oscillator and the second local oscillator. The second local oscillator is also about 80 megs, but it's got a narrower range, and that mixes down to 455 kilohertz. And then the final oscillator mixer pair is for carrier recovery. That's a 7-ish megahertz oscillator that divides by 16 in order to generate a signal close to 455 kilohertz in order to re-inject the carrier and recover the speech on SSB. On transmit, that signal path is reversed, and you have a Vogad mic amplifier which injects into the what was the last receiver microprocessor and becomes the first, rather the last mixer, and that becomes the first transmit mixer. And so you go back through at 455 and at 83 megahertz, and then it's mixed back to the HF band, and that transmit signal is lifted in power by a couple of drivers, and then a push-pull power amplifier lifts the level to 50 watts. There's a harmonic low-pass filter, makes sure that a compliant signal is radiated, and you can see the antenna is on the top left-hand side. You can also see that there's a loudspeaker and audio amplifier just beneath that in order to bring the receive audio signal out. So that's the system diagram. And here's a diagram of the receiver gain distribution. You'll see the oscillators that I mentioned before, LO1, its frequency range, LO2, frequency range, and the carrier insertion oscillator. Gain distribution is important in realizing low intermodulation distortion and achieving the AGC performance that is desirable. And you can see inside the blocks it tells you specifically what kind of components are used in order to realize the gain. The first IF amplifier at 83160 is identical transistor, identical gas FET as used in the commutating mixer. ATF-13736 from Hewlett-Packard was what was used in the earliest days, although later NEC transistors were used. You also see Mini Circuits Era 3 was used as a gain block, and the Philips TDA-1572 was used as the AM receiver IF gain block. That has two internal stages to it. Now the first mixer, very critical component, and it was decided to use effectively a passive commutating mixer using gallium arsenide FETs as high-level perfect switches. These have very low on resistance and absolutely minute capacitance, and so they're almost ideal switches. The gates are driven very hard in antiphase, and the FETs actually have no DC supply, so that the signal path is reversible. It's similar in principle to a diode ring mixer, but better in terms of intermodulation distortion. This slide addresses the topic of intermodulation distortion as relating to the first mixer component. It's very critical that you achieve a good third order intercept. Basically, intermodulation is a phenomenon whereby two out of band signals can mix in order to produce an interfering in band signal. It's very common in the HF domain to have strong broadcast stations that are some distance in frequency from your wanted receive signal. For example, if you have a strong broadcast carrier running 50 kilohertz high of your wanted signal, and another one 100 kilohertz high and containing modulation, you will hear that modulation on your wanted frequency if the receiver that you're using has a poor intermodulation performance. Now this slide shows how that works. If your receiver is tuned, say, to 7042 kilohertz, and you've got a strong carrier running on 7062 kilohertz, say at minus 20 dBm, and then another 20 kilohertz up from that on 7082 kilohertz, you've got Radio Tirana. That used to be the national station of Albania, which typically ran very high power levels. And say if you're getting that at minus 20 dBm, then the intermodulation product in the first mixer will produce a signal at 2 times 7082 minus 7062, which is 7042, your wanted frequency. And if the performance of your receiver is poor, you will hear Radio Tirana. Now, that is a big deal, and in fact at QMAC we built a useful little marketing device. It consisted of a double balance mixer, effectively a double sideband transmitter, and into that double balance mixer were injected two signals. One signal was from a crystal oscillator just running a carrier, and the other signal was from a crystal oscillator which was injected into a double balance mixer, acting as a double sideband transmitter. And the other port of the mixer was fed with an audio signal from a recording chip. The two oscillators were combined in a passive combining network, and so the resulting device created this intermodulating interfering signal that was not on the wanted channel, and so if it was plugged into a radio with good intermodulation performance, there would be no degradation of a weak received signal. However, if it was plugged into a competitor's radio, of which there were several, which had poor intermodulation performance, then the signal would be degraded by hearing this message of the off-frequency transmitting interfering signal. So this could cause a great deal of embarrassment to competitive companies, and the QMAC radio had a sufficiently good intermodulation performance to ensure that when the device was plugged in, there was no interfering signal heard. So this graph shows plotting third order response, and you can see the plot has input power in dBm versus output power in dBm. The third order intercept point in this particular graph is at plus 20 dBm output, and you can see it's extrapolated. So the fundamental response, which is a slope of 1, crosses with the third order response, which is a slope of 3. So the thing about third order intercept is that as the signal level increases in the interfering signals, the effective blocking rises at a rate of 3 to 1 rather than 1 to 1. So when you get into trouble, it happens quickly. This block diagram shows phase lock loop frequency synthesizer. You have the master oscillator, the divide by R counter yielding the reference frequency FR. The phase comparator then feeds the loop filter and then on to the voltage controlled oscillator, giving the oscillator frequency F0. That is fed back through a divide by N counter to the phase comparator. Now both the divide by R reference counter and the divide by N counter are fed from the microprocessor, and that determines the frequency that the radio is set to. For example, when the VCO is set to 83 megahertz and with a step size of 100 hertz, the divide by N counter would then be set to 830,000. Now in this arrangement where the step size is at the reference frequency, you get very poor lock times and narrow loop filter bandwidths. Now this is bad from the point of view of phase noise, because when the loop bandwidth is narrow, there's no cleanup occurring, and also when the loop bandwidth is low, the lock time is very poor as well. It's much better to use a system called the magic number system, which I think was originally developed by the Canadian Marconi company. In this system, you allow the reference frequency to vary over a relatively wide range, and the HF-90, that's about 40 kilohertz to 202 kilohertz. You then tolerate a small frequency error, say about 5 Hz, and then you can compute values for the R and N counters which will satisfy these conditions for each frequency step, and you store these in a ROM. This leads to rapid lockup, a broad bandwidth rather than a narrow bandwidth, and low phase noise. So it's a very good system, provided you've got a limited number of steps, which is the case in an HF radio. This slide shows the circuit diagram of the first local oscillator. That's a voltage controlled oscillator that covers quite a wide range. You'll see its push-pull configuration, and it uses 2 JFETs. It's a Hartley, and you've got varicap diodes, but you've also got effectively a clamp that limits the excursion. This is a relatively high level oscillator running at least 10 milliwatts, and that yields a low phase noise. Another feature that contributes to that low phase noise is using that hard clamping with the red LEDs. You'll see the 4 red LEDs. They limit the swing on the gates of the oscillator. This is much better than using, say, a Zener or some other characteristic, say, of the FET itself in order to achieve the limitation. LEDs are very good in that the noise that is yielded from an LED is very, very low relative to, say, a Zener junction. So that's a feature that you'll see maybe in 1 or 2 radios. Raycal used that system. This slide shows the loop filter of the frequency synthesizer. On the left side you'll see a type 2 loop filter, 1 capacitor C99, and then an RC combination R25 and C96. That then goes on to a non-linear amplifier. Now, non-linear amplifier is important because the transfer characteristic of a varicap diode is very non-linear. And without a non-linear amplifier in cascade with that characteristic, you'd end up with a relatively uncontrolled loop gain and possible instability. So this is overcome by having inverse characteristic non-linearity achieved by this amplifier here. Now this is effectively a voltage to current converter. You've got a current source in the tail of the long-tailed pair FET transistor pair there, and then you have got effectively a current squeezer up the top. You've got a current mirror, and current comes out of the Q15, Q14 junction there, and that is fed into a non-linear network that consists of a number of resistor diode pairs, and these resistor diode pairs are effectively a piecewise linear approximation feedback network where the resistance is effectively switched according to the voltage on the series network. So effectively you've got a load that is non-linear on that non-linear amplifier, and that feeds out to the varicap diodes. Here you see the more general circuit diagram of the frequency synthesizer. A dual synthesizer chip from Motorola controls both the first and the second local oscillator. The first local oscillator is a push-pull configuration, the second local oscillator a single-ended one. Up in the top left-hand corner you'll see the signal strength meter. That uses a digital to analog converter in a feedback network in order to estimate what the AGC voltage is at any one point in time and convert that to an 8-bit digital word. Now up in the top right corner of this slide, you'll see the microprocessor of the HF-90. That's an ATC51 chip. It has a 74HC574 address latch there. You've also got non-volatile memory to contain the channel information. And at the bottom of that there's a TCXO, which is the master oscillator. Now the design for the microprocessor in the HF-90 is truly minimalist, and it took its inspiration from the simplicity of the Sinclair computing ZX81. That you've really used an absolute minimum number of chips, only used 4 chips, and it did this by reusing the ports extensively and also using wire-OR configuration. The HF-90 uses serial shift register outputs in order to simplify track routing, and just like the ZX81, the maximum work is done by software. The CPU works extremely hard and does the work that in other radios are done by lots of other chips. So money is saved, it's kept simple, and it's easier to service. And this slide shows the serial control chain. It's a cascade of shift registers. It makes the signal routing, the digital signal routing, relatively straightforward because it's just the standard I2C type 3-wire system. And that reticulates things like the light emitting diode display values, miscellaneous digital analog converter values, the volume DAC values, and also the PA filter switching coefficients. So that's a system that also loops back in order to check that you have got continuity on this serial link chain. As I mentioned earlier, the PA, the RF power amplifier, is relatively simple in design. Both the driver and the final amplifier are push-pull. They both use MOSFETs. And the final amplifier uses IRF-830 MOSFETs in most of the radio serial numbers. That MOSFET is a general use MOSFET, high voltage, 500 volt MOSFET, 1 amp, and that is run at 50 volt rail. That leads to a relatively simple output matching requirement because 50 volts at 1 amp is 50 ohms, so it goes directly out. There's no need for step up or step down. It's within a feedback network in order to stabilize the gain with frequency. You have got a resistor into the gate and a resistor round from the drain to the gate. This slide shows the characteristics of the RF-830 MOSFET. Now the one characteristic that has to be overcome in this MOSFET is the input capacitance, because obviously that is shunting the input, and as the frequency rises, this becomes an effect that effectively decreases the gain of the device. So it's important that the driver has a very low output impedance and it's effectively able to drive that large capacitance. This slide colourfully illustrates the use of mass technology parts in the HF-90 design. Now the design rationale was to use as many devices as possible that were thrown up by the technology, the consumer technology revolution of the 1990s. We saw the emergence of mobile telephones, satellite TVs and computers. These gave rise to cheap frequency synthesizer chips, cheap surface acoustic wave filters, cheap gallium arsenide MOSFETs that are very suitable for HF radios as well as satellite TVs and mobile telephones. So you see on this slide you've got a cheap microprocessor, and very readily available microprocessor, the ATC51, available from at least 7 different vendors, relatively cheap non-volatile memory chip, frequency synthesizer beneath that from Motorola. And then the front end has gallium arsenide MOSFETs, initially from Hewlett-Packard and latterly from NEC. And the surface acoustic wave filter at 83.161 was available from a number of vendors, including Toco, and that initially was a through-hole device and later on became a surface mount device. And of course, the block filter, again a Toco filter, available at 455 kilohertz SSB bandwidth. So that concludes this presentation on the design of the HF-90 radio. There'll be another video that I'll make on frequency hopping design.